you realized that microorganisms, specifically fungi,
Mm-hmm.
could break down one of the most forever plastics that's in existence today.
Yes.
I'm Nick Ebling, founder and CEO of Not Impossible Labs. For the past 15 years, we've been on a mission to change the world through technology and story by addressing societal problems to improve the lives of everyone. With a crew of engineers, hackers, entrepreneurs, technologists, storytellers, and artists, we've tackled and solved some of the world's most incredible challenges. But here's the thing, we're just a small team in Venice Beach. The world is full of people making the impossible possible. My goal now with this podcast is to find these people, share their stories, and hopefully, together, we can keep pushing the limits of what's possible. On today's episode, we talked to Dr. Amira Samat, who has discovered an earth-grown solution to our global plastic crisis. You just broke down the forever plastic, polypropylene. This is about, for us, taking complicated subject matters like the work that you are doing and boiling it down so that brilliant people like yourself can talk to not so brilliant people like me and make it so that your incredible work is something that other people might be able to understand. We're going to talk about the work that you're doing. We're going to talk a little bit about that day, that moment when all of a sudden things transition from impossible to not impossible, and then everything that led up to that point. Thank you for joining us. So let's just jump right in. I am joined with Dr. Amira Samat. How did you get interested in what you're doing? Because we're going to talk with you today about yourself and Dr. Ali Abbas have been working on this absolutely groundbreaking approach of being able to break down plastic, specifically polypropylene plastic. This is the stuff that is in medicine bottles and carpets and clothes and plastic furniture. This is the gnarly hard plastic. This is not just the thin, flimsy plastic water bottles. And you have figured out a way to break that down organically. So I want to talk a little bit about that. But what was the, when you were a little girl, how did you say, I want to study fungus?
I have been interested in science since I was a kid.
What kind of science? What was the first science that you got really fascinated with?
Biology, of course. And because when we did primary school, we experimented on how trees grows and how animals reproduce and something. And then when I did my bachelor's degree, I selected biotechnology as my degree. So when I did biotechnology, I have been exposed with a lot of biological experiments like environmental sciences, marine sciences, and how these animals interact with each other, and how pollutions destroy our environments. What sorts of environmental effects that actually affect the reproductions. So among them are, of course, pollutions. And then when I did my PhD, where everything comes to a very specific, specific sets of knowledge. I can't do broad research anymore. So my supervisor, Prof. Ali Abbas, he actually suggested me to utilize microorganisms. And this microorganism is to be used to, degrade plastics. And the very first thing of his idea is he wants me to test this effects of this microorganism on all types of plastics. But I can't do that. It will take forever to actually test on every types of plastics. So he asked me to focus only on one. And I choose one of the hardest plastic, which is polypropylene. And fortunately, after few failed attempts, I finally, are able to select some of the microorganisms that, I can see that, they can degrade plastic, and specifically polypropylene. So yeah, I can say that that is a very relief moment. I can't say I'm like overjoyed because I was doing my PhD, so it's a very stressful period of my life. But yeah, I'm happy. It turns out great.
You just glazed over this. Oh, so I was doing this, and my professor suggested this, and it worked. That's what worked. That's a pretty big deal, right? So, what was the moment? What was the moment you started this? And some of the details is that so you started working with your concoction, your witch's brew of fungi and microorganisms and bacteria, and you made this little melting pot. And then within 90 days, you can degrade polypropylene plastic by 27%.
Yeah.
And you can break it down completely within 140 days. Is that correct?
Yeah.
Okay. You are so calm and you are so nice. You just broke down the forever plastic polypropylene.
This is the not impossible moment. Polypropylene is one of the toughest plastics out there. For decades, scientists believed it just doesn't break down, at least not in any meaningful way. Amira proved otherwise. With a mix of fungi and bacteria, she showed that polypropylene can degrade by 27% in 90 days and could theoretically disappear completely in about 140. The forever plastic suddenly wasn't forever anymore.
So let's walk through what you actually do, because what I understand is that the process, and you talked about it, is the first you have the fungi and the bacteria. And those are basically fairly common bacteria and fungi that's found in soil and vegetation and different things like that. They're going to decay complex organic materials. Is that right?
Yes.
Then you go through a pre-treatment process. And correct me if I'm wrong. If I say anything that's not correct, correct me if I'm wrong here. Okay.
All right.
So we take the plastic, the polypropylene, and we treat it with UV light or heat or Fenton's reagent.
Fenton's is an oxidizing mix that rusts things at a micro level. Translation, it scuffs the plastic so microbes can latch on.
Is it or is it and? Do you do all of those things, or it's one or the other or the other?
One and the other. We didn't combine them all. We test 3 different kinds of pretreatments.
Okay. And so then you take that, you pre-treat the plastic, and then you introduce the microorganisms.
Yes.
And how do you introduce the microorganisms? Is this just a piece of plastic in a test tube? Is this in a big bowl? What does it look like? Describe it to us what it looks like, and what's the size, what's the magnitude of the experiment?
First, we have to take a conical flask. I'm not sure if you're familiar with how it looks like.
No.
So the conical flask looks like a cone at the bottom, straight. It's like a cylinder opening, and then at a cone at the bottom. So we put the fungus first and the media that can support the fungus or bacterial growth. And then at the same time, at different place, we pre-treat the plastic using this heat or UV or Fenton's reagent. So after the pre-treatment is done on the plastic, we introduce the plastic. We put the plastic inside the conical flask where there is a fungus or bacteria inside there.
Okay.
Right? And then we cover them, and then we place this flask in the incubator, like the oven size incubator. And then inside there, we control like the temperatures, the humidity, and then the RPM, where we shake this flask constantly for 30, 60, and 90 days. So, when we have like established the condition, the temperature and everything, then after 30 days or 60 or 90 days, we take out the flask, and then we take out the plastics, like whatever remains, and then we test them, and then we weigh and then to see how much it has been degraded. That's it.
And does the plastic turn into a marshmallowy goo?
Well, there's something you don't see every day.
Or is it just start to reduce its size? What does it look like?
Normally, for example, if we use the film, like polypropylene film, you can see that there are like damage. You can see that the plastic has been it's not in its original how do we say condition. You can see like some has been some parts has been washed off, some has been accumulated with the fungus on top of it. So it means that they have created like the environment where they can live on the plastic and they can consume them. It doesn't turn into like a gooey marshmallow or some of them like break into pieces, but they still remain the plastic form, if you can say that. But it has been like the condition is not similar before and after.
Here's the simple loop. Plastic pieces go into a shaken flask with nutrients, then into a warm incubator. After 30, 60, and 90 days, you weigh what's left and repeat it all over again.
Now, obviously, the plastic is something it's led to a lot of great things in this planet.
Yeah.
But it's also led to some bad things, right? It's led to things like the giant floating, island of plastic out in the middle of the ocean. So you've got this great Pacific plastic patch out there, which is the size of, to put it in the terms of geography, it's about the size of Mongolia. It's about the size of Alaska, right? It's 3 times the size of one of our states here, Texas. Now, this is a blight on humanity. It's blight on the environment. And what you've created now obviously gives hope to the fact that this man-made plastic might be able to organically, through the microorganisms in the process that you've developed, might be able to just return to an organic state. The process that you just described, though, is first you're heating up the plastic, then you're introducing the plastic, you're introducing fungus to the plastic, and then you're shaking it repetitively for 90 days.
Yes.
Right? Not something we can't really shake the state of Alaska for 90 days.
What's that? Earthquake!
Or Mongolia for 90 days. But where do you see the practical, pragmatic implications of what this could lead to in terms of dealing with non-recyclable forever plastics?
The thing is, as I mentioned before, this is like a very fundamental study. My supervisor and I, we actually want to scale up these processes. And we want this process to be able to be used commercially. And in order to do that, we have to conduct another set of experiments using a pilot scale reactors. So we want to scale up from just incubator, just a conical flask, into like a huge a huge bioreactor. So this bioreactor looks like a huge tank, where we fill up these media, we put in the fungus or the bacteria, and then we put in the plastic all together, and then we just shake them. But in using bioreactor, we don't shake them. We have like a propeller inside it to make sure that the aeration process is consistent throughout the durations. So currently in Sydney, my supervisor is in a process of doing that. So and we are also in a process of patenting this system. Together with like my colleagues and his co-researchers over there to finally like have a scale-up system. So when we have this, I believe that we can use this system and apply it in any parts of the world, in a recycling facilities or even in landfill. So we can have like an in-house system that can just degrade the plastic on site without the hassle of doing it in a small scale or wasting resources.
So eventually we don't need to pre-treat the plastic. Eventually we don't need to shake the plastic. Eventually this works in landfill. Is that where you see this going? where
Yes.
you can actually introduce the fungus to landfill, walk away, and you come back in 141 days and or more. But it is now it's returned to the earth. This
Yes.
soil-based fungus has now returned it to a soil-based organic
Yeah.
material.
That is like the ultimate dreams, I can say. But of course, like in order for us to have this a scale up system or like a comprehensive system to degrade this plastic, uh, probably something has to be done to the fungus or to the bacteria to enhance
Right.
my capabilities. So let's
Sure.
say if we finally end up, genetically modified them, so it can't be released to the environment. So yeah, that is like another concern, but not today.
How did you discover the right concoction, the right titration of fungus? Like, how did you I'm just imagining you as a crazy mad scientist late at night in your mixing bowl, in your petri dish, mixing this. How did you come up with the right titration?
Right. Okay. Well, I must say that we have faced a lot of failures at first. We have tried to isolate before we publish these two fungus. If you can see the Aspergillus and Angiodontium album, these two has been published. So these two are actually selected from the literature. I looked into the literature. I saw that some of this fungus has been used and some has not been utilized to degrade polypropylene. So that's fine. We did that and we achieved a good result. But when we go into a different objective of the experiment, I try to isolate the new microorganisms. So that's when failures happen. When we try to select this microorganism, the hardest thing will be, because we select this from the marine water from Sydney Harbour. Okay, when we did this, we got a lot of microorganisms on our plates, and we can't use them all because it will be hard to identify which species is responsible to degrade. So we have I think 20 to 30 different microorganisms on the plate because they have a different structures and morphologies. So we
This is from the Sydney Harbor.
Yes, from the Sydney Harbour.
So you just went out to the end of the pier and just dropped a bucket in and grabbed a bucket of water and brought it back to the lab.
Actually, no. We have a friend, a friend from a Seabean project. I'm not sure whether you've heard of Seabean project, where they actually have it looks like a pail where they deploy it into the ocean and then it will suck in plastics. Have you heard of it? Yeah. It is.
No.
It is a very good initiative because I think they are the NGO organization, not parts of the government or something. So they put this bin in Sydney Harbours and they suck a lot of plastics, and they gave me this plastics from Sydney Harbour, and I took this plastic and isolate the microorganisms that are attached on the plastics. So technically, these new isolates comes from this Sydney Harbour, and they are able to settle down on these plastics, on this plastic waste. So I took this, and then we got 20 to 30 different kinds of microorganisms. So we actually we select the most dominant one that we can see on the plate, and then we did a screening test whether this microorganism can survive in a media full of plastics. And then finally, we actually got 2 to 3 that can survive in this during the screening processes. But in the end, we only select one fungus and one bacteria that are able actually to degrade more compared to the one that you have read in the literatures.
So it was a competition. It was a fungi race, basically.
Yes.
Right? It was a seeing which one is going to win, and then eventually you took the one that won, and that's what you used.
Yes, exactly. We see that this one can survive better in the plastic environment, and then we test them and see, oh, okay, this the degradation rate is much higher than the one that we have before. But unfortunately, I can't disclose the name of the new isolates, that the one fungus and one bacteria, because we try to patent the process and these microorganisms. Yeah.
Wait, so you're saying you've got top secret information and you're not willing to reveal it on this podcast?
The figment of your imagination.
I want to, but I can't.
Amira, we demand, our listeners demand, you must reveal today.
Oh, well, I want
What is it? How about this? Let's just play the guessing game. What does it rhyme with? Just tell us what it rhymes with.
God. I don't.
By the way, if you can figure out what it rhymes with, because I read the names of the fungi that you used, and here goes. Don't laugh at me.
Okay.
Aspergillus terreus and Engydotium album. How did I do?
I give you like a B+.
Oh, all right. Let's hear how it's actually said.
Okay. The first one is Aspergillus terreus.
All right, that was close. I was at A-. All right.
Yeah.
What's the last one was a D. That's what. What's the last? What's the second one?
Okay, the second one is the Engyodontium album.
Yeah, I didn't get close on that one. Amazing.
Much more interesting thing is that these fungus are isolated from marine water, so they can live in a salty water, in a salt environments. So in a way, let's say if we don't apply this in a landfill, it is a good news that we can actually degrade plastic in the oceans. So that's why we want to do.
There it is. There it is. We can take down this gigantic floating country of plastic that's living in the ocean. Now the ramifications of that are almost incomprehensible, right? Like the fact that you could do that, but there goes back to what you were saying, is that we have to make sure that what you're creating isn't now going to kill every fish in the ocean.
Yes.
Because what you've created, we got rid of the plastic, yay, and there's no more fish, boo, right?
Yeah, exactly. That's why we need like a system, a closed system first.
You need more than 140 days is what you need. I'm not going to tell you your business, but we need to experiment for longer than 140 days.
Exactly, yeah. To be able to release such microorganism to the environment, it must take a lot more. We need like an ethical approval or something. So that
sure. Yeah. How long? And I know we're having fun talking about this, but how long do you think something like that takes to bring to market, in your opinion?
Well, probably 2 to 3 years.
Okay.
Yeah.
Still significant. That's in our lifetime. You can foresee, a solution to this massive problem.
Yeah. At least before I die, I can see what I've done, have impact to the environment.
Sure. Incredible.
And because this research only focuses on polypropylene, as you can see. Sure. So in a way, we really hope that it can be applicable to other types of plastics too. And my supervisor, like Prof. Abbas, wants to focus now on microplastics, which has been like a huge headache towards the oceans. So we look forward to work on that after this. Yeah.
As you realize now that the microorganisms that you're working with are attacking polypropylene, we've been studying and looking at PFAS and a lot of the microorganism work. As an organization, we've been very fascinated with PFAS and just the concept of forever plastics and forever chemicals, and obviously leading to microplastics as well. And the studies around that, about the fact that every single human has some sense or some sort of microplastic within them now. If this podcast does nothing except for introduce brilliant people to each other working with similar passions around the reduction of forever chemicals and forever plastics, that would be fantastic.
Oh, great.
I find it ironic and very narcissistic for humans to think that we've created anything that the world can't eventually gobble up and spit back out in 200 or 300 years once we're long gone from now. But for the fact wouldn't it be nicer if we were able to take the mess that we've created, polypropylene and PFAS and the forever chemicals and forever plastics, and actually do our part now while we're alive to start that degradation process like you're talking about, and to do it at scale? That seems like an incredible dream that you have.
Oh, thank you so much. Yeah, I mean, before we started the experiment, of course, we want to like do something that are beneficial to everyone, like to to our everyday lives, not just doing like a very advanced research where no one understands. So yeah, and I must say that we are almost there, although not 100% yet. But yeah, we hope that when we like optimize our processes and finally found out what is the best or the most suitable condition for this fungus to grow, or whether these kind of pre-treatments are no longer needed, or whether we need to enhance more the pre-treatments, and ultimately we will, fully degrade them, any kind of plastics. Yeah.
What else should we know? Is there anything else that you want to share with us today that we didn't talk about?
Well, about the experiment, not much, but I can say this. Whatever we have done now is not like the ultimate solution to the plastic problem. I think everyone is aware of that. I mean, it is exciting that we are able to find like the light at the end of the tunnel. Like we can do something about the plastic pollution that we have now, but it doesn't give us like a license to pollute the environment even more. Because I'm sure that when some of the people think that, okay, we have a solution to degrade plastic, so we can now use plastics, like there's no tomorrow, something like that. So I just want to make like everyone aware of this, that we still have to play our role, to reduce the amount of plastic that we put into the environment, into the landfills or into the oceans. We still have to reduce our usage, because even though like we finally had set up the system, we have come up with a solution that we can degrade the plastic in 1 month, for example. We still have like a lot of plastics in the world that is waiting, to be degraded, like in the landfills or even in the ocean. Like you see, in the size of Texas, I don't think we can degrade everything in 1 month if it is the size of Texas or Alaska,
Right.
So yeah, everyone has to play the role. We have to reduce the amount of plastics, and then you can help us to, take this plastic and then degrade it using the microorganisms that we have known or we have experimented that, are able to degrade much more.
And that wraps up another episode of the podcast, where we talk to some of the most fascinating people who are transforming the impossible into the not impossible. A big thank you to Amira for sharing her discovery and exploring ways to create a cleaner future. It's conversations like these that remind us that solutions to our toughest challenges might already be growing all around us. Don't forget to follow us on your favorite podcast platforms. And remember, change is hard, but making the world a better place, it's not impossible.